Okay, let's start our class. So just recap what we have learned in our previous lecture. We learned to calculate the percentage of solid and liquid from the phase diagram. Okay, so when you see this kind of question, normally it will give you the element name. Um, the element normally is fixed, but important is from the graph. Temperature and percentage of the element. All right. So here it will give you like a curve of copper, Cu. So here is Cu, right? Then it will give you temperature. Given temperature of interest, so let's say A. So you come in from A point. Then of course there's some curve there. So what you need to be careful is that you need to identify where is the liquid and where is the solid. Then if you're given the A, you identify the 2 points, you draw a straight line. Then after that, the element will be given a certain percentage. For example, 55%. So 55%, after you look at the question, you go to the graph, and then you look for 55% of that element. For example, 55% of copper and something. So you go in 55% here, and then you draw a straight line up. Right? Then you mark another point. Then you have a few length. So you have length B, length C, length D. Right? So when he asks you at 55% at temperature A, how many liquid, how many solid? The percentage of weight in liquid, when you see the word liquid, you pick the point near to the solid. So you take D length divided by B. All right. So if the question asks you percentage of solid at 55% at temperature A, you take 1 minus the previous one. Or you take C divided by B, like near to the liquid region. Okay. So it gives you a few points of interest, right? Identify where is liquid, where is solid, and then where is the interest temperature and also the question interest percentage, right? So you draw, and then identify the total length, identify the liquid to the point of interest, the solid to the point of interest, and then you take the ratio, right? Your answer, when you take the ratio, is just a maximum is 1. But when you see the question asks you in percentage of weight, you need to times 100 to get percentage. Okay. So we go through a few examples previously, right? So we have flipped the chart. One is liquid on the top, solid on the bottom, and then also we did some example of liquid at the bottom, solid at the top, right? But the concept still same. Concept still same. Then today we learn something new. Okay, example 1, 2, 3, same procedure. Right. Now, previous 1, 2, 3 is equilibrium. Equilibrium means stable state. What happened today? We learn about 9.6, which is non-equilibrium. Non-equilibrium. There's this one. In some cases, the state of equilibrium is never completely achieved because the rate of approach to equilibrium is extremely slow. Such a system said to be non-equilibrium or metastable. Because the cooling or the temperature you want to reach there is very, very slow. and you want to see the liquid state, solid state very, very hard or very, very slow. You need to wait for some time. So it fall under non-equilibrium category. All right. So in non-equilibrium, the atomic diffusion is very, very small. So an extensive period of time is required to eliminate the concentration of gradient. All right. So for example, you will see something like that. So when you see this one under microscope, you see like a mountain from the satellite image, then very high chances this one is under non-equilibrium. All right. So we want to see how core structure form. Okay, I'll give you all the slides. So we consider mixture of nickel and copper, 70-30%. Is cooled from a temperature, initial temperature T is 0 at the rapid rate. So on the left-hand side, you see the temperature and percentage of copper. Percentage of copper means the more you go, the more copper you have. Right? Then on the right-hand side is a copper, percentage of nickel. So the more you go, the more nickel you have. Then identify where is the state, liquid for the right-hand side diagram, liquid on the top, solid at the bottom. Then middle, alpha means solid alpha. Alpha means solid alpha plus liquid. Then on the left-hand side, liquid on the top, and then you see the equilibrium and non-equilibrium. So the blue line is equilibrium solid, that is we cover in example 1.3, previous lecture. But today, if the temperature was cooled down in the more rapid rate, means more faster rate, so it will follow this blue line, black line. So we have a non-equivalent solidus, right? Okay. Everything is almost the same. Only now, today, this session, you'll see a new line appear on the phase diagram, which is the black line. Okay. So basically, you see what is different between left and right. The right-hand side is what you've seen previously, right? So we just flip the chart, right? Just flip the chart. Okay. So let's examine what happened to that each individual point. So at point number 1, T1 here, you see, because you see this side is solid, right? So when you drop from very high temperature to T1, it will form on this one. This is two phases line. This blue line is two phases, because why? It can be either alpha liquid or solid alpha. Right? It can be two phases here. Okay. So composition alpha 1 means if you drop down, you see a percentage. Then you rapidly cool down. You see the two dot here. One equilibrium one is a bit lower, but rapid one, you can see solid a bit faster compared to the blue line, the black line here, right? So you can see, So what happened to A prime 2 and A2? You see here, when you drop from T1 to T2, you form a alpha prime 2. You have an extra layer outside alpha 1, means initially it was in the molten state, right? Then you cool down, you will form a A2 concentration or A2 layer outside A1 when you rapid cool down from T1 to T2, right? Then on the microscope, you will see that actually they start to grow some nucleus, right? Some solid like that. So you have alpha 1 covered by alpha 2. It will grow bigger and bigger. But you see that actually you see a few layers. In this case, if you drop from T1 to T2, you see 2 layers. Okay. And then the remaining one, the white color blend space here is a liquid. Right. So overall composition of T2 is between A prime 2, A1 in A2, and you can denote as A prime 2. So A prime 2 is between alpha 1 and alpha 2. Is between these two values. Right? What is that? They ignore this line. So since the timeline, okay, recall what is timeline? This horizontal line is called timeline. This is called timeline. Right. So since the timeline of alpha L2 is longer than alpha 2 L2, alpha L2 and alpha L2. Right. So what does it this statement line? We measure L prime 2 to L2 a bit longer from here to here, a bit only. You see a difference? If you measure L prime 2 length from here to here and here, alpha 2 to L2, you have a small differences, but alpha prime 2 will be longer than the normal one, equilibrium one. Okay? So what does it mean if we have more length? So I enlarge the two line. So the blue line, alpha 2, and then the black line, somewhere here, a bit higher here, alpha prime 2. So until another side of the blue line or equilibrium line is here, L2. Just mean that so here is solid, here liquid, here between here is alpha and liquid. Here, this black line, when you pass here, only becomes solid. So here you will have here to here will have alpha and liquid also. Right? So that's why you see on the slide there, it mentioned when you rapidly cool down, you will have more liquid compared to the equilibrium one. Okay. Okay. So solidification will be delayed at that temperature by rapid cooling. So if you do rapid cooling, you have more liquid compared to the normal one. Okay, so I write, maybe I write the black color. Oops. Can understand? So this one is alpha plus liquid. So there's more more length compared to the T2 lah. Okay. Then as the temperature lower from T3 to T7 here, the same process of also happen. So this process is called non-equilibrium process. Okay. So as you go deeper and deeper, lower and lower temperature, it will be covered by alpha prime 2, 3, 4, and so on. So as you rapidly slow down, you have more and more. It will go bigger and bigger, but you see layer by layer. So at T6 here, the solid freezing had less copper than the original composition of alloy, which is 30%. So here at T6, if you drop down, the percentage of copper that you have is lower than the equilibrium temperature. If you T6, you move down here. So here you have more copper compared to less copper. And so on. So temperature 7 is stopped here. Average composition 30%, and the freezing is complete. Okay. So we want to eliminate this kind of behavior with its core structure. So the ingot, previously when we learned about process, ingot or casting are heated to elevate temperature to accelerate the solid state diffusion. This process is called homogenization. Right? Okay. So how does homogenization heat treatment? It must carry out at a temperature that is lower than the lowest melting temperature or the melting occur. Right. So this one is play with the temperature. So temperature just below T7 should be used lah. So here is non-equilibrium. This one is equilibrium. Okay. The rest you read. So there's a boundary the form when you cool down the metals. Okay. So the red color here is a normal equilibrium process, which is this call. So we pull this zone and then we enlarge it. We pull this zone out and then we enlarge it. So, and here you see on the top is liquid, bottom is alpha, means solid. And then you have a point B and so on. So here, if the temperature was given again, you draw a line, you have liquid and solid. So you're given a certain reference composition, you draw that line out. You should able to find how many percent of solid if you use this length, and how many percent of liquid if you use this length compared to the total length. Makes sense, huh? Okay. So if you compare side by side, equilibrium is what you learned before this, right? So let's say we take a nickel cases. So again, left-hand side is equilibrium, so it's a normal process. On the top is liquid, on the bottom is a solid. Then this one is a mixture of solid and liquid. Right-hand side is non-equilibrium. And you can see there's a shift of line. There's a shift of the red line was squeezed inside, right? And the diagram also show you how it formed. Okay. Now, non-equilibrium, the biggest difference, if you look at the diagram, you will see like a layer. It's like a tree, the tree line. You chop the, sorry, you chop the, so the direct comparison between two is that for non-equilibrium, you see layer on the solidified solution, right? It still apply to the same basic of understanding. Yeah. Okay. Yeah. Yeah, because I don't want to load you with too much information. The finding of how many percentage of liquid solid still same. You only look at the diagram, then find again, you're entering temperature, your initial percentage of composition, and then find the total length between solid and liquid, and then find what is percentage of liquid, percentage of solid at that particular composition. Okay. So far, we are looking at a binary system. The binary means two type of material. Okay. Now we have a limited solubility. This graph, this chart is very, very popular for engineering dynamics, especially when it comes to assessment test 2 and also your final exam. Okay, so previously we looked at copper. Now we look at lead and tin. So as you look at the graph, go bottom of the graph and see what is this graph mean. This is percentage of tin with this SN. So means the more you move to the right, you have more tin or SN. So as you can see here, identify where is the liquid, where is the solid. Of course, if you download the tutorial question in Canvas, you will see this graph. Right? You can open, you can use your handphone and go to Canvas and download the tutorial PDF document. So you will see this graph on the tutorial question. So identify where is the liquid, which is solid. So as you can see here, on the top here, more liquid liquid. This top layer liquid, and then as you go down, you know that as you cool down the metals, you get more solid, right? So temperature, you cool down, and then alpha means solid alpha. Here is a mixture of alpha beta. Beta liquid here is beta plus liquid, alpha liquid, and so on. Okay. And we will start introduce you a few technical word for binary system. Okay, so let's start with okay. Let's start with the top diagram here. Let's pick a line here, this dotted line. Alloy 1, alloy 2. So here, let's move. Okay, alloy 1. There's one point here. It's called eutectic point. Eutectic point. If you put your finger here and you stand here, you will have a mixture of lots of things. You have a mixture of beta, you have a mixture of alpha beta, you have a mixture of alpha liquid, beta liquid, and also liquid at this point. Okay, this point is called eutectic. So if you look at the microstructure, you will see there is a eutectic alpha and beta over here. This is alloy 1. Then, and this one, eutectic point happen at 61.9% of tin. 61% of 0.9% of tin, and minus 100 this one. So you have another side of PB. Okay, so when you look at binary system, your answer will always have A percentage of something, and then B percentage of something. Okay. So let's look at this line. So one important point from the binary system is called eutectic reaction. Happen at 61.9% of tin, SN, at what temperature? At 183 temperature. So you can see there is a straight line over here. It's called tie line. Very long tie line there. And when it comes to your assessment, always look for the tie line. You'll be given that one temperature, look for the tie line. Yeah, so at eutectic point over here, you have alpha 19.2% SN. This one here. Beta 97.5%, and liquid and so on. Liquid 91.5%. So there are some calculation to get this one. We're going to show you how to get all these numbers. But from this graph, what you know at this eutectic point, you have alpha, you have beta, you have liquid. What's at this point? You have liquid, you have beta liquid, you have alpha liquid, and you have alpha beta. So you have a three. You try to find the three things here lah: alpha, beta, and how many percent of liquid. Here is just a highlight, just to be sure what meaning of the blue line that you see on the graph. Right. First, look at the axis. Then, how many percent of element? Here you have two elements, PB and SN. And then look at the line. What happened? What meaning by the line again? Where is solid? Where is liquid? The solid, what kind of solid you have here? Two kind of solid, alpha and beta. Okay. We will start to dissect this diagram. So the region of restricted solid solubility of each end of a PBSN diagram is designed as alpha and beta phases called terminal solid solution. Where is this statement say? If you look at the diagram, you look at the far left and far right, the space that you have. On the left pocket, you have alpha. On the right pocket, this very small pocket here, you have beta. They are in solid 200% beta. On the right, this is full 100%, you have alpha on the left pocket. This is called terminal solid solution. Okay, terminal solid solution, which means if you want to find the eutectic point, you try to find where is your left pocket, right pocket. In this case, you have alpha this point, right pocket beta at this point. Okay. So if you look at alpha phrases, blah blah blah, solid maximum 19.2% of SN. How to find 19.2? Here 0% means 100% of PB. Until here you drop down, you get 19.2 or 20% of SN. Okay, so from here there's a range of it depends on what point you're looking at. Okay, same with beta phrase on the right hand side pocket. So here, if you drop down, you will see 97.5%. 95% of SN. And you take 100% at 2.5% of PB. Okay, so here to here is a thin rich solid solution and can dissolve a maximum of 0.25% of PB at that particular temperature. In this case, it's 183 degrees. Okay. So means the percentage of these two element is called solubility, the maximum solubility. Yeah. Okay. Okay. So far, okay, right? This graph. Okay. Now we start to look at one side of the graph first, and then we enlarge. Right. Because in your coming test or final exam, you need to explain what you have. Right? So let's look at the far left of the diagram. So here, on the top liquid, bottom is alpha beta, and on the left pocket you have alpha solid, and then alpha here. The graph give you alpha solid and liquid, right? So if you look at this line, this dot line here, if you drop the temperature from the top to bottom, you see there's a formation from point A, point B, point C. You see the difference of solidification process. On the top liquid means there's nothing there, 100% liquid. In the liquid there, you have how many percent of SN? How many percent, weight percentage you drop down and you read from the x-axis here. Okay, you drop down and then you read how many percent of SN you have. Right, C1 percentage. Then you reach B. B, you have alpha and liquid here because it's inside this small region. It's inside here, right? So you have alpha and liquid. So you should able to draw the schematic diagram. If I give you 1 point on the phase diagram, you just label, you draw a circle or you can draw a square, no issue. Important is you label what is inside that particular point. For example, point B, you draw alpha and you label L at the space there. Okay, then if you drop down, you see 100% of solid, you just draw alpha, fill in the, or even you don't need to draw the boundary condition, you just draw the full and then you write alpha, also correct. Right? Okay, so yeah, so this one, if you drop from the top point A to C point means you cool down the thing, cool down the thing. And then now you shift the line from C1 percentage to C2 percentage. You shift the line, C2 percentage. Now your C2 is at here, and you drop your temperature from D, E, F, and G. Same. Identify where is your liquid, and then the dot, where does it land? This one, it land in alpha liquid, so you draw here, alpha liquid. Then E drop to F. F is a full solid alpha, so you just draw and then draw alpha. Then F drop down, you'll see alpha beta, so you label your alpha and beta. Okay, or you can just draw some space, label alpha beta also can. You don't need like draw the blue dot, as long as the diagram show that you have. Okay. Okay, now we start with some calculation already. So far everything okay? All right. All right. Now we start to dissect what is eutectic point. So there's a specific alloy composition known as eutectic composition that freeze at a lower temperature than other composition. The lowest temperature at which the liquid phase can exist when cooled down slowly is called eutectic temperature. So we want to find the eutectic temperature. What is eutectic temperature? It's the lowest temperature at which the liquid phase can exist when cooled slowly. What does it mean? You look at the liquid diagram, liquid space, and then you slowly drop down the temperature until you see the first solid appeared in the microscope. Means you start to touch the liquid, the solid line. For example, any region also works. For example, I pick the alloy one. Alloy one here is liquid. You drop. Then at this point, you start to see solid already appeared in your microscope lens. So this point is called eutectic point. Same if here. If you drop, here you start to see alpha already. And then here also you can also can technically you can say this one also eutectic point. And then you start to cool down and so on. Okay. So you have to be specific on the temperature that you're entering. So, okay. So here again, where is your eutectic temperature? It's the lowest temperature where you see solid. So if I compare alloy 1 line and alloy 2 line, just now I say that point B also eutectic, right? But it is not eutectic. Why? What is eutectic is the lowest temperature. Point B is not the lowest temperature. Point B is around 250, but this point, alloy 1 at this point, is the lowest point on the graph that gives you the first solid. Okay, if you drop, it means you take your ruler, you drop until you see the solid. The liquid phase can exist when cool down. You look at lowest temperature, look at liquid phase that can exist. You drop from liquid, then you drop. When you still can see liquid, is still you still go down. But if you pass this point, this is already solid. Here also solid already. Here you still have some liquid, but it's in a straight line. So this is the eutectic temperature. Very important, huh? This eutectic temperature in the exam, we don't tell you what is the temperature. You need to read from graph. Okay. So again, how to find eutectic? You identify where is the liquid phase. Use your ruler. You drop down, slowly drop your ruler. You see where is the lowest point of the liquid phase. Because all these are solid already. So you drop until you see the lowest point. You see one lowest point. That is called eutectic. You draw a straight line to the left and then identify, write that one as eutectic. Then you copy. You write in your answer eutectic temperature equal what? Okay. So on this graph, PBSN system, where is the eutectic composition? Again, what is eutectic? Is the lowest temperature you can go when there is still liquid phase exists. So at this phase, you drop down, there's a point there. That point, you drop down, you see the percentage.
You give the point in the
No, you draw a ruler to the left. You read from this scale. Huh? Oh, how you know this this temperature, is it? Okay. Okay, I'll draw something on the whiteboard. Let's say I create some new graph. Okay, I'll draw. Let's say I give you a new graph that okay, this is temperature. This is percentage of something. Let's say, I don't know, copper or something. This one maybe nickel or something. Then, okay. This you familiar with this one. Liquid, solid. Let's say I give you alpha here. Here, normally alpha and liquid. So what is eutectic again? Eutectic. What's the definition of eutectic temperature or eutectic? The lowest temperature where the liquid can exist, right? So liquid, you drop your ruler, drop here. This is your eutectic point. Because why? This is the lowest temperature you can go when your liquid can still exist. After this one, cannot already. You see, this is eutectic temperature. Okay. Why this alloy tool, this dashed line, why point B is not eutectic? Because it's not the lowest temperature yet. This eutectic point is more lowest than point B. Okay, okay. The concept is important. Once you understand what is eutectic, then the rest is fine. The graph is it can change. The graph it can change. Okay, then you read the percentage eutectic composition. Like on the graph that I draw on the whiteboard here. You just drop down here, find the percentage of copper. So here it will give you percentage of copper, let's say 10%. And also 90% of nickel, for example. Okay. It depends on what the question want to ask you. Okay. Important when you look at the phase diagram, temperature and composition. Okay. The rest you already same eutectic point. Where is the eutectic point? Okay, so far everything good, Okay, I think we have a here. We'll continue 9 o'clock.